Okay, so on the quiz, number 2. 27 randomly selected subjects are given the test. Their mean score is 76.2 and their standard deviation is 21.4. Construct a confidence interval.
That's a means.
Means or, yeah, that's a means problem. How do you know?
Because it says math.
Because it says means, right? It says the mean was this. So you know, oh, it's a means problem. 1 sample or 2? 1 sample. And it's a confidence interval, so to get a confidence interval for 1 sample mean, you use t interval, right? Third one, part C. Grocery store wants to determine if there's a difference in shelf life between 2 brands of donuts. So they take a random sample of 100 of each of those kinds and determine the shelf life. Using the results, they conduct a significance test, whether there is no difference in the mean shelf life. Means or proportions? Means. I didn't hear anybody answer. Right? Do you see how easy that decision is a lot of times? It's just, if it has the word mean in it, it's a means problem. And they won't always have the word proportion, but if they don't, they'll have percentage. And it's really the same thing. Okay? So people just get in a hurry, or they get test anxiety or something, and they use all kinds of procedures on things when, you know, if you just look and see, well, this is a means problem. If it's means, it's got to have what in it? T or Z? T. If it's a means problem, it's got to have T in it. Right? If it's a proportions problem, it's got to have a Z and prop. Right? It'll have prop Z. Okay, so that one is 1 sample or 2. 2, and are they independent or dependent? They are independent. You've got a box of 1 brand of donuts, a box of another brand of donuts, and whether this one molds doesn't have any effect on whether this one molds. Right? So they are dependent. So that's 2 SAMP T test, because you're doing a hypothesis test. Okay, D says we have a percentage of 12th graders who have tried marijuana in 2003. And you have a sample p hat of 46.1% versus 42.7% in 1991. In 2003, they surveyed 14,600, and in 91, 15,000. Construct a confidence interval for the difference between the population proportions. Means or proportions? Proportions. 1 sample or 2? 2. Difference in proportions. There's got to be 2 of them. Right? So it's 2 sample proportions. You don't really have to ask the next question, which is independent versus paired, if it's a proportions problem, because we just didn't cover that. Right? So you only had independent samples. So what's the procedure? 2 prop Z int. Okay, next one, 12 subjects are asked to test their grip strength, each on consecutive weeks. I won't read the whole thing. Is this a means problem or a proportions problem? It's a means problem because it says mean grip strength. Construct a confidence interval, so you know you're going to have an int on the end of this thing. Or is it 1 sample or 2 samples? 2 samples. You got a classical music sample and a rock and roll sample. Now, are those samples paired or are they independent? They are paired. How do you know they're paired? Because I wrote it on your quiz, which means you missed it, right? So now, how would you ignore that? How do you know? What is it in there that tips you off? Oh, this is paired data. Paired data always looks like what? 2 measurements made on the same subject, right? So it says, the key sentence is, strength was made, during one of the tests, the subjects wear headphones playing classical music. During the other, listen to rock and roll. Which order they hear the music is determined at random. So So, oh, they're each hearing both kinds of music in a random order. So each is being measured twice. That's paired data. That was probably the most commonly missed one on this quiz, is putting 2 SAMP t-test there, or 2 SAMP t-int instead of, what should it be? T-interval on the differences. I didn't take off if you didn't write on the differences, but that's good to keep in mind. Okay, the last one. You've got 6th graders, 7th graders, and 8th graders, and whether or not they have tried smoking. What kind of a test is used there? Data is in a contingency table. What's the kind of test we used for contingency table? What'd you say? Chi-square test? Chi-square test, good. So, and if there were only 2 rows, like if we were only comparing 7th, 8th graders and 8th graders, you could do this as a 2 prop Z test, but now there's 3 of them. There's P1, P2, and P3 for 6th graders, 7th graders, and 8th graders, so then you have to go to the chi-square test, which handles any number of proportions. Any questions? On the test Friday, okay, hang on just a second. On the test Friday, you'll have a series of questions. They'll be worded similar to this, and you have to figure out, okay, which procedure am I supposed to use on this question? And if you get the wrong one, you just lost a lot of points. So practice this. That's why I make a quiz out of it, right? Because if you can get all of these the right procedure, then the only mistakes left are just little ones for entering the wrong numbers or whatever. Right? Okay, Elijah, what was your question?
The answer to E.
The answer to E?
Yeah.
That should be T interval on the differences.
It's just T.
T interval. Yeah, there is no 1 SAMP T. I wish there was, but they call it T and then 2 SAMP T. Okay, so let's get to the last new material before this test, and that is section 11.4, which is comparing 2 population proportions. So already you should know what you're going to use for hypothesis test on your calculator before I ever tell you. I think there might have even been one on here. No, there wasn't. I didn't have a test, but I had the hint. What's it going to be? What do you think?
2 prop Z test.
2 prop Z test. See, you can already figure this stuff out. See, you're getting so good at this, you can anticipate. This is going to be more of the same stuff, different procedure on the calculator. Right? Now, I will warn you, this topic in the book, they go through the whole rejection region thing again, and on the online homework, they wouldn't let me not select that. So you don't get to use p-values. You have to use the rejection region. On the test Friday, you'll get to use p-value. You can use either one you want, but I recommend the p-values. And when you're in this homework, and we'll do one straight out of the homework, when it says make the decision, then you can look at your p-value to make the decision, right? But you still have to tell it the correct rejection region. Okay, so there's a little bit of formulas, as there always is, to get through before we start on this. Kind of the preliminary upfront stuff, and then we'll just start working problems. So, assumptions necessary for this to be valid. This is part of step 2. Remember, step 1 of a hypothesis test is state the null and alternative. Step 2, determine the correct distribution or the correct procedure, and then see if it's valid. And this is seeing if it's valid. So first one is always random samples. Those samples, now we've got 2 of them. They need to be independent, right? So not paired data. We will not cover the paired data case in this class. If you're interested, sign up for 343, Applied Statistics. We do it in there. Conditions for a binomial distribution are met. Remember what binomial distribution? You're counting the number of successes in a fixed number of trials. Those trials are independent. You've got 2 outcomes and only 2 outcomes on each trial. Right? So success is failure. As long as you're meeting those conditions, then that's appropriate. And then the last one is your sample size requirement. You've seen this before, so you're used to how ugly that looks. What does it say in English? 5 successes, 5 failures in
Both trials.
both samples, right? Both samples. So with the ones in p hat 1, in p hat 1 minus, whatever, that's sample 1, this is sample 2. Right? So you have to have 5 in it. Okay, so the hypotheses, the book does it both ways, and the calculator does it different than this, just like it did for means. Some of the book problems will have it written this way with a difference, P1 minus P2, and sometimes they'll do this, P1 equal P2. Right? Algebraically, this is exactly the same as P1 minus P2 equals 0. Just subtract P1 from both sides. Right? So, calculator will want things like this. Some of the homework problems ask for it this way, some of them this way, but it's really easy. It's obvious because they put the symbols for you, and all you do is pick the equal sign or the not equal sign or whatever in between. You'll see. Oh, we'll do one in a minute. Right. So just like before, the null is either an equal sign, a greater than or equal, or a less than or equal, but it always has an equal. The alternative never has an equal. It's either a less than, a greater than, or a not equal. Right? There's one difference. Before I go to the next slide, let's review a little bit of confidence intervals, since you got to do those on the test also. The standard error for confidence intervals for 2 proportions. See if you can remember this. I don't expect you to remember it, so I'm going to write it. See if this looks familiar. Does that look familiar? Okay. So this is for confidence intervals. For tests, it actually changes a little bit, because when we do hypothesis testing, we always compute everything assuming the null is true. And if the null is true, then P1 is equal to P2. So these two are the same. And if they're the same, your best estimate is to ignore the grouping variable, like your population. If you have males and females or whatever it is, pool them together. So this P bar, they call the common population proportion, or pooled estimate. So P bar is x1 plus x2 over n1 plus n2. What's x1 and x2? Okay. Number of successes in the first sample, number of successes in the second sample, and then the total pooled sample size. The number in the first plus the total number in the first plus total number in the second. Okay. So this is the pooled estimate of P. Your calculator will compute this for you automatically, but it doesn't use a bar, it uses a hat. So what the book calls P bar, the calculator calls P hat, with no subscript. So your calculator will give you P hat 1 and P hat 2, but it'll also give you P hat with no subscript, and that's the pool. So you'll see what that is in a minute. So for tests, the standard error is P bar, 1 minus P bar over N1, plus P bar, 1 minus P bar over N2. It looks really similar But notice that now it's the pooled estimate of P in there instead of P1 and P2. And then algebraically, since that's the same term in the top of both fractions, you could, if you wanted to, factor it out. And this is the form the book gives it to you in. So that's all I'm doing is factoring out this common factor on the top of both of those, factoring it out front, and then you're left with just 1 over N1 plus 1 over N2. So that's the format they put it in the book. Your calculator does not spit out the standard error as part of the output when you do the 2-prop Z test. It does spit this thing out, but it won't give you this. So if you're asked for this, you've got to have this formula and know how to use it. I don't think I'll put one of these on the test, but I'm not sure about the online homework. They may have a place where they want to see that standard error. I actually don't think they do with hypothesis tests, and they do this one for confidence zones. So test statistic, that's about as pretty a formula as you're ever going to see. Look at that. It's got P's all over the place. But it's just the same old story. What is P hat 1 minus P hat 2? What is that called? Point estimate. Point estimate of what? Of this. Right? The population difference. So the sample difference in proportions minus the population, the hypothesized value of the population difference over standard error. When you divide by the standard error, you standardize it, you get a Z test statistic. You get a Z-score. Now, what is the hypothesized value if the null is true for this second part? 0. So you can just take that off. So it's just P1 hat minus P2 hat over the standard error, and you got your Z test statistic. Your calculator will compute the Z test statistic and spit it out for you. So you don't have to plug stuff into this formula to get that number. You just run the 2-prop Z test on your calculator and write down or enter into the Hawk system the Z test statistic that it gives you. Right? So we're going to let you rely on technology rather than memorizing formulas to get some of this stuff done. Okay, so rather than work this problem as a example problem, let's go right into the Hawk's system. Now the thing that I'm worried about here is that since I did this for my other class already, that I won't get to, it won't let me re-enter the system to work the same problem over again, but we'll see. If it doesn't, I may have somebody volunteer to come up and log into theirs, and we'll just do the practice one, so you don't get credit for your homework. Okay, I'm going to skip that one. I want one with a scenario to it. Perfect. This is a good one. So it says a salesman for a new manufacturer of cell phones claims not only that they cost the retailer less, but also that the percentage of defective cellular phones found among his products, P1, will be no higher than the percentage of defectives found in a competitor's line. To test this statement, they blah, blah, blah. So we'll come back to that. Does the retailer have enough evidence to reject the salesman's claim? So the salesman claim is that P1 is no higher than P2. How do I write that? P1, P2, right? P1 is no higher than P2. Less than or equal to. No higher. Higher would be greater than. So that's a null statement that they give us there.
What if you do
What?
isn't it less than?
No higher. Yeah. I'm just seeing if anybody's watching. One person was. Nice. So this is the null because it's got an equal sign in it. So what's the alternative? Greater than. P1 is greater than P2. So here's what I was talking about earlier. They let you know which form they're putting these in, at whether it's the difference or the symbol goes in between, because they give you the P1 and P2. All you do is pick the symbol. So the null, I can't even see what we wrote over there. Which one did we pick? The bottom one. No higher would be less than or equal. And then the alternative is greater than. The opposite symbol. That's right. All right. Next. Find the values of the two sample proportions, P1 hat and P2 hat. Round your answers to 3 decimal places. How do we do that? What's P1 hat? Or what is, in words, P1 hat is the good number of successes, which we'll call X1, over the sample size, which we call N1. And so that, how many successes did we get in the first sample?
60.
Okay, the salesman is P1, right? So the salesman's cellular phones and a random sample of 150 of the salesman's phones, 120 of the competitors, 16 of the salesman's. So you got to get all the salesman's stuff together. So this is 16 over 150. So, as I do every once in a while, to me, this stuff gets hard when you're reading a whole bunch of information all at once. Just start organizing. When the first number you come to, I mean, what did they just give you? The retailer took a random sample of 150 salesmen's cellular phones. If I'm calling the salesman's sample 1, then that's N1. So you write down, N1 is 150. And then the next number is 120. That's the number they sampled of the competitor's phones. Oh, that's N2, 120. And then the next two numbers are the X's. So 16 is the successes for the salesman's, and 9 is the number of successes for the competitor. So then you can get these easy enough. P2 hat is 9 over 120. And we're supposed to round those to 3 decimal places. Sometimes there's a way to make this so it will take fractions. Anybody know how to do that?
You put your first number and then you do divide, and then you have to arrow down.
Using the keypad?
Yeah.
Okay, so let's try that. That sounds fun. 16. And then keypad.
No, just hit
like
the.
on your
Oh,
put a slash.
I thought you meant you had to.
No, sorry.
So just hit the slash.
You have to click on it.
Slash.
Where it asks for decimal places, I don't think they'll allow fractions.
Well, that was a good try. So give me the decimal places.
0.107.
Okay, let me write it up here. 0.107, and what's this one? 0.075? Okay, 0.075. Oh, wrong order. 0.107. 0.075. Love their little happy faces. Compute the weighted estimate P bar. Okay, here we go. Let's do that one by hand real quick, but then we're going to do it on the calculator as well. So how do I get P bar? Did I erase P bar? No, it's under here. P bar. X1, X2 we have right here. Then N1, N2 we have right here. So P bar is 16 plus 9 over 150 plus 120, which is 15 over 270. Oh yeah. I'm bad enough at math in my head, and when I'm standing in front of people, it gets even worse. All right, so what's that? Point what? 0926, and we're going to need to round to 3, so that'd be 093. Right? Now, what do you notice about that number compared to these two numbers? It's about in the middle of it. It's not exactly in the middle because the sample sizes aren't exactly the same, but the number you get for P bar should always be in between those two. If you get a number that's not in between there, look at your answer, see if it makes sense, and go, oh wait, it ought to be in between those two. You catch a mistake that way. Okay. So 0.093. Great job. Step 4 says compute the value of the test statistic. Oh, remember that horrible formula? It's time to bail. Grab your calculator. Go to 2 prop z test. You'll do that by pushing the stat button. Then go over to tests. And down to the 6th one, which is 2 prop z test. Now, notice on this procedure on the calculator, it does not have you enter the null hypothesis. Because it forces the null hypothesis to be P1 equal P2. It won't let you test that the difference is something else besides 0. But all of our problems are set up that way anyway, so that's okay. So then you've got these 4 numbers to enter. All right, so X1, N1. 16 over 150, and then X2 is 9, and N2 is 120. Now, P1, and then the calculator is saying this, P1 colon, and then it has a not equal P2, a less than P2, and a greater than P2. You look back over at your alternative hypothesis, and you pick the one that matches. So that's greater than P2. Select that one, press enter, and hit calculate. Now, all the way at the bottom of the first page, there's an arrow, so there's more stuff down there, but there is a P with a little hat over it. Everybody see that? That's this P bar. Calculator calls it P hat, the book calls it P bar. But notice it's the same number. Right? So that's a good check there, 0.09259, rounding to 093. Then at the top, we get the test statistic Z. So Z is 0.892005. And we're supposed to round to 2 places, so 0.89. Now, before we do anything else, is that a big number or not so much? What is a test statistic again? What does it tell us? It tells us number of standard errors that our sample data is from the null hypothesis. So the test statistic will have a standard normal distribution. Right? If the null's true, then we would expect to get 0 for that test statistic. Okay? Halfway down the hill is out to where? 1 and -1. Remember, it's standard normal, so it has a standard deviation of 1. So where's 0.89?
Not quite one.
Not quite to 1. So our p-value is going to be that area. Okay? Greater than symbol, so it's right-tailed test, so it's only that one tail, the right tail. So that test statistic is not very big. We're going to fail to reject the null hypothesis. But look at the p-value. This shaded area is 0.186195. And that's the p-value. Remember what a p-value is. It's the probability you could get sample data like you got, or even more extreme, if the null is true. So it's just the shaded area out past the test statistic. Okay, so let's go ahead and enter, and I want to use that picture for the next part of this. So I guess let me just erase this and we can look at it on the screen there. 0.892, or no, well that was not a 9, 89, just 2 decimal places. Submit. And got that right. So we go to the next part, and it says determine the decision rule. And this is the part I don't like. What is decision rule? Well, that's that rejection region that they like to do. Right? So reject the null if, and then it has a box with a little arrow, another box with a little arrow, and then a place to enter a number. Right? So to figure that out, we need our alpha level. So alpha is 0.05. And I'm going to erase my shading here, but use this picture. How far out in the tail is far enough to reject the null? If the p-value were, our p-value is 0.186, so we're not going to reject the null. But we would reject the null if what?
If your p-value was less than alpha.
If the p-value was less than 0.05. Well, how far out do I go before that happens? In other words, what's the value of z that has 0.05? How do I find a value of z that has a certain area to the right? Yep. What were you saying, Dorlin?
Inverse something.
Inverse something. And this is a z distribution, which is a normal distribution. So inverse norm, right? So this z critical value is the rejection region that they're wanting. So z critical value is inverse norm. Now you can enter alpha. If it's a one-tailed test, you just enter alpha, but it's going to give you a negative number, and then you just ignore the negative if it's a right-tailed test. Or you can put in 1 minus alpha, or 0.95, because that's what area is left of it. Right? So either one. So I'm just going to do the 0.05, so I don't have to do the subtraction. It'll give me a negative. What does it give? 1.645. You go to 3 places. And then we just ignore the negative. Make it positive. So that's my rejection region. So I'm going to reject the null if z is greater than 1.645. So So let me pull this down so it'll show up. Reject the null if, and the two choices that you get are z with no absolute value bars or z inside of absolute value bars. When do you use the absolute value bars? Two-tailed test. Because then you have to allow the possibility of getting a z on either side, so you just make them both positive and work on the right tail, so you take the absolute value. But this is a one-tailed test, so I'm going to use the z with no absolute values. So pick that. Then the next little arrow is greater than or less than. We're going to reject if we are out there, so that's greater than z. And then the number is the 1.645 that we compute. Now before I hit enter on this, if you don't have, I guess everybody's got inverse norm, right? I start to say if you don't have, you can click on the tables and you can get that, you can pull up a z table to get that number. But since everybody's got inverse norm, that shouldn't be an issue. So we'll submit that. We'll get to the next part. Ooh, fantastic, it says. All right. Now this kind of makes me mad about the Hawk system too. They didn't finish this thing out. This is step 6 of 6. Make the decision of the hypothesis test. And all it says is reject or fail to reject. On my test Friday, what am I going to have after this step? And interpret that. What does that tell me about the salesman's versus the competitor's cell phone lines? Right? Some sentence that addresses the context of the problem. So we'll do that after we finish this. Which do we do here? Fail to reject because our p-value is 0.186, which is not less than the alpha level. So we're going to fail to reject the null hypothesis. And we got that right. So now, write out the conclusion. That'll get you full points. What can we conclude about our cell phones? Good. That sentence always starts with there is or there is not sufficient evidence. So here it is, the word not. There is not sufficient evidence to conclude, and then you always state the alternative hypothesis. To conclude, and I erased the alternative to write this, but the alternative was P1 greater than P2. So to conclude that the percentage of defectives, the salesman's percent defective is greater than the competitors. Okay? You don't have to word it exactly like that, but the main thing I'm looking for is that you address the context of the problem in the correct manner, and you either say there is sufficient evidence or there is not, depending on what your p-value is, and you write the alternative value. Right? So usually they'll have a sentence that they claim. They claim that, and then you can address that. But here the claim they gave was actually the null, so you need to switch it so you're addressing the alternative. Okay? All right, well, I want to do one more thing. Remember from our class data, when we did the chi-square test, we used this example. And we have a 2x2 table here with smoke and non-smokers as the rows, and then exercise non-exercise as the columns. Well, if I want to test the claim that there is a difference in the proportion who exercise, well, let me write this out. Test the claim that there is a difference in the proportion, I'm going to abbreviate, of, and non-smokers are on the first row, so I'm going to use non-smokers as group 1. That's completely arbitrary. But proportion of non-smokers and is a difference in the proportion of non-smokers who exercise and the proportion of smokers who exercise. I'm abbreviating there all over the place. Okay, so test that claim. I want you to do it. Here's the data. So first step is to come up with your null and alternative hypothesis. Second step, pick the right procedure to see if it meets the assumptions. Third step, do it. Get your test statistic, get your p-value. And then step 4, make your conclusion. And I want the conclusion the way we had written that one as a sentence. Okay? And I'll come around and check on you as you're going. So if you have a question or you get stumped, just call me over. These slides will be posted so you don't have to scribble everything down here into your notes. You can get this later. Just get to working on it. Almost not use. Oh. Okay. Yes, good. Yep. Okay, got it. Okay. Oops. Okay. Good. Okay. No, I don't think that's right. Okay, I think you've done some wrong. Go back in and let me see what you entered. Yeah. 206. You used the column totals for N. You need to use the row totals for N. Anybody have any questions? Is this your hypotheses? Okay, this one, that's not right. Do we have a direction stated? No. Even though we kind of know there is a direction to this, I didn't state it that way. That is correct, only it's not area, it's P's. It's a proportion. Okay, that's good. Okay, you got numbers? Okay, good. Those are right. Okay, so those look right. But this is right. Okay, we're just about out of time, so I'm gonna hurry you along. The null hypothesis, it looked like everybody was getting, it is P1 equal P2. There's no direction stated, it just says is a difference. So the alternative would be P1 not equal P2. Right? And instead of me writing it out, I have them on the following slides, so I'll just go through the slides. Let me leave this behind. there's the hypotheses written in the other form, but that's the same thing. And then here's how you should enter the data. X1 206, N1 326, X2 12, N2 39. Right? It's a not equal symbol, so then you hit calculate, you should get this output. What about that p-value?
Really?
Very small, so we have sufficient evidence to reject the null and say there is a difference. Now, one thing I want you to see before we go, we did this test as a chi-square test before, and the test statistic we got was 15.221. The test statistic today was 3.901. If you take that number and square it, you get the chi-square test statistic. Mathematically, that is cool. And you get the exact identical p-value. So the chi-square test and the 2-prop z test are identical tests for 2x2 tables. It only works for 2x2 tables, but mathematically they're exactly the same test. So you've got two ways of doing the same thing, but they're equivalent to each other. All right, we'll see you Wednesday.